Greetings and welcome to episode 9 of the Math Olympiad Lecture series. Today we will be introducing the concept of functions, one of the big ideas in mathematics. The objective of this lesson is to give an introduction to the topic of functions. The success criteria for students will be to be able to find the range of a function, to be able to work out the inverse function, as well as the composite function of simple functions. A function is a relationship that maps a set of input values known as the domain to a set of output values known as the range or the codomain. For example, let's take a simple function like f of x equals to x plus 1. This adds any input value by 1. This function will map the input value of 2 to 3, so we can write f of 2 equals to 3, and so on. An alternative notation is this arrow notation, which is basically the same thing. Functions can be classified into two types. One-to-one functions are where every input has a unique output, like in the case of 2 to the power of x. This is in contrast to many-to-one functions, where two different inputs may result in the same output. What is nonsensical is a one-to-many function. It is strictly forbidden for a function to map one input to more than one output. In these two graphs drawn here, we have a linear function fx and a quadratic function gx. We define the domain of the function as the values of x that the function can take. For a given domain, the range will correspond to the inequality that represents the possible output values of y. In these two simple examples, this inequality bounds the graph within some maximum and minimum value. With those definitions out of the way, let's have a look at question 1. Find the range of the function f of x equals to x squared minus 6x plus 14 for the domain x is between 1 and 8. Take some time, pause the video here, and give this question a good try. A helpful strategy when dealing with functions is to sketch the graph so that we can explore the problem visually. By plugging in the values x equals to 1 and x equals to 8 in the given function, we can find the starting points and ending points of the graph. The problem arises when we think about how the function behaves between the start and end point. This is where the previous lecture on completing the square comes in helpful to determine where the turning points of the graph lies. In this case, it happens to lie between the start and end point. One more thing to note is that when you're stating the range, you have to be careful with the inequality signs. This function's range is strictly less than the maximum of 30, but it is more than or equals to 5. So, did you get the answer? Now let's move on to the next concept. Inverse functions. Think of this as an undo button. It takes the function's output and finds the original input that maps to that particular output. Also note that only one-to-one functions have inverse functions. In the course of your math education, you'll come across many examples of inverse function. Take the example of function f, which doubles a variable. The inverse function would be one that halves it. If the function gx is one that is an exponential function, the inverse function will be one that is a natural logarithm. In trigonometry, the inverse function of sine is literally called the inverse function of sine. This explains the confusing nomenclature of that -1 superscript that resembles a reciprocal. But wait, aren't you thinking that the sine graph is a periodic function? How can it be a one-to-one function? Shouldn't it not have an inverse? Well done if you're thinking of that. That is why in trigonometry, we begin the chapter with the concept of the principal values. The principal values of the sine graph lies between -90 and 90 degrees. This is the domain of the sine graph that allows the graph to behave as a one-to-one function. Let's have a look now at question 2. Given that f of x equals to x plus 1 divided by x minus 3, where x cannot be 3, find the value of 2016 multiplied by the inverse function of negative 7 over 11. Pause the video here to give this question a good try. Now, the strategy here is to work backwards. If the inverse function of x gives us a, then f of a should give us x. Substituting a into the function, we get a plus 1 over a minus 3, which must give us back the original x. Making a the subject of the equation, we get a equals to 3x plus 1 over x minus 1. This gives us the inverse function. If you put everything together, we will get a result of 1120. Graphically, if we sketch the original function fx shown here in blue, the inverse function shown here in red will be a reflection of this graph across the y equals to x line. So, did you get the answer? The last concept today is composite functions. Let's look at the example below. Suppose we have two functions, f and g. F of x is equals to 2x minus 1, and g of x is equals to x squared. Fg of x is a composite function such that we perform the function g first on x, followed by the function f. If we wrote it as gf of x, we will have to perform the function of f first on x, followed by the function g. Generally, the order matters for composite functions. As shown in this example, fg of 2 will give us 7, whereas gf of 2 gives us 9. Let's have a look at question 3. Given the function f of x equals to 1 plus x over 1 minus x, find the value of this expression below. Note that when we write f with a superscript 3 or 5, this is the same as writing f of f of f of 5. Pause the video here and give this question a good try. In times like this, we can only rely on a bit of brute force, but in the hope of some pattern. If you just try and evaluate f of 5, f of 5, and so on, you'll be rewarded on your fourth iteration, which gives you back the original input of 5, the number that you started with. What happens now is that each successive iteration of the composite function will begin to repeat the values. While the first 4 terms will give us a sum of 119 over 30, the first 2016 terms will give us 504 sets of 119 over 30. This gives us a total sum of 1999.2. The last 2 terms of this series will give us negative 1.7, and this gives us a total of 1997.5. Multiplying the entire result by 2, we will get a total of 3995 for the expression that we wanted. So, did you get the answer? Here are today's extension problems. Solutions to Lecture 8's problems have been updated into the info section of the previous videos. Here's problem 3 and problem 4. We have come to the end of episode 9 on functions. Do like the video and subscribe to the channel to stay tuned for more episodes. Episode 10 will be covering continued fractions and other recursive functions. Thank you and have a good day of learning.